Okay, we're continuing in 8.2 with semiconductor doping. Impurities are added to intrinsic semiconductor materials to improve the electrical properties of the material. The process is referred to as doping, and the resulting material is called an extrinsic semiconductor. That's vice the intrinsic semiconductor we talked about previously. There are two major classifications of doping materials. First of all, there is trivalent, and materials that come under this category are aluminum, gallium, boron. And these are materials that have 3 valence electrons, and has some pictures to come in future slides here. Then there are pentavalent materials, things like antimony, arsenic, and phosphorus, and these are materials that have 5 valence electrons. Pentavalent and trivalent materials. These materials have essentially the same structure as silicon, except that they have one or more or one less valence electron. Okay, so they either have one more or one less valence electrons. These materials, when mixed, and this is where we get the term doped, with the semiconductors, appear to create a defect in the lattice structure. And so here we have, this is a pentavalent atom here, and you'll notice that there are 5 electrons in the outer valence shell. Now this is a trivalent atom here, and you'll notice that it has 3 atoms in the outer valence shell. Now you'll recall from a previous lesson we saw that pure silicon, when it was in its lattice structure like this, it had 8 electrons in its outer shell. Now if we mix this pentavalent material in there, there's going to be an extra one. And if we mix this material in there, there would be a lack, there would be 7. So, and some examples here, pentavalent, antimony, arsenic, phosphorus, and trivalent, boron, aluminum, and gallium. Okay, trivalent doping. Silicon is the most widely used semiconductor material. By adding a trivalent material to the crystal structure, holes are introduced and provide a mechanism for conduction. Because trivalent materials can accept an additional electron, they are called acceptor atoms. A silicon crystal doped with trivalent material is called, and here is a term, P-type material. P-type material, and this is a result of trivalent doping. And so here's the process. We start out with intrinsic silicon. Then we add trivalent atoms, and what do we get? P-type silicon. When doped with trivalent material, holes are created in the semiconductor valence band. The doping impurity in this case is aluminum. So here we see the lattice structure that we see in silicon, except that here we find an aluminum atom. Aluminum has 3 atoms in its outer shell, and so what do we get? Instead of having 8 here, now we have a hole right here, and here's another hole right here, and then here is another hole. And so we got our lattice structure. This appears to create an impurity in this, because we did have this nice this nice balance system, 8 everywhere, but now every place that we see this aluminum atom, there are going to be 7 and not 8. Pentavalent doping. Doping silicon with pentavalent material results in extra electrons being available, improving the conduction characteristics. Pentavalent materials donate electrons and therefore are called donor atoms. Once the silicon crystal has been doped with pentavalent material, it is called, and here's another term, Ntype material. Ntype semiconductor material. And here is the process, same thing. Start with intrinsic silicon. we add pentavalent atoms, and what do we get? N-type silicon. Impurity doping material phosphorus is added to the silicon. Note that valence shell is full with 8 electrons, and the extra electron is now available. It's now called N-type material. So here we have the nice silicon lattice structure until we get right here to this phosphorus guy. And since he has 5 electrons in his outer shell, the outer shell is full with 8, and so now here we have that extra electron. And then here's another extra electron, and here's another extra electron. These are all associated with that phosphorus atom that was mixed in and making our nice silicon impure. It's got this phosphorus in it now. Okay, we want to take a look at energy levels both in P material and in N material. Now, we have this image up here. In fact, this is available for this particular part. I didn't have it when we talked about this previously. But we have here we have P-type semiconductor and we're looking at absolute 0. Now, up here is what we'll call the conduction band, and this represents free electrons. And then in this lower level, we look at the valence band. What is available in the valence band? So, we're looking at P material first. At absolute 0, all electrons are at their lowest energy level. There are no conduction band electrons. Okay, so there is no energy. Okay, no energy available, so there's nothing going on in the conduction band. Note that there are holes in the valence band, since there are not enough electrons to fill all the holes. And you remember that when silicon is doped with trivalent material, it actually reduces the number of electrons in the valence shell. So at absolute 0, there's going to be holes present, without any energy whatsoever. There's going to be holes because that's just the nature of the material. At room temperature, okay, this is room temperature over here, and this is P-type material, the electrons receive thermal energy, and some of them break their covalent bonds and move to the conduction band. This creates a hole in the valence band. So what that's saying is that here we have, we have this silicon, and it has in fact, remember that there isn't all, many of them still have 8, but it doesn't make any difference. But at room temperature, there's going to be energy available, and some of these electrons will move to the conduction band, which would be in this band here. Now, this creates a hole in the valence band, so this will create additional holes in the valence bands of our P material. Now, because of the presence of the trivalent material, there will always be more holes in the valence band than electrons in the conduction band. Now remember, when we looked at pure silicon, we had an even number of electrons as holes. But with P material, there will always be more electrons in the valence band than more holes in the valence band than there are free electrons in the conduction band. Okay, energy level in N materials. Now here we're just looking at the same thing again, only we're considering N material at this point. At absolute 0, okay, no energy. There are no holes in the valence band. Okay, notice there's no holes in the valence band, and free electrons are available in the conduction band. The covalent bonds support a max of 8 electrons. The impurity material will add 1 extra electron and is forced to a higher conduction level. So remember that with the N material, the lattice structure was completely full. In fact, there wasn't an extra electron there. So at absolute 0, you have the 8 electrons are bound into that the valence shell, but there's an extra one. So even at absolute 0, there are extra electrons available for conduction band. Now, at room temperature, some of the electrons will break away from their valence shell and move to the conduction band. This will create holes. Okay, so at room temperature, remember we still got our 8, and what we're going to find is that at room temperature, some of those will become free electrons, and so we'll have, and we will have some holes created as a result of that. Okay, as a result of pentavalent impurity, there will always be, and note this, more free electrons in the conduction band than holes in the valence band. Okay, now let's review what we've said here. We started out talking about semiconductors, and remember, this is a pure semiconductor. They'll have equal numbers of free electrons and holes. Okay, remember we had that the nice balanced atom that had 8 electrons in it, and for every free electron there was going to be 1 hole created, and they had equal numbers of each. Now, with P-type material, now this is doped with trivalent material, we'll always have more holes than electrons in the conduction band. Okay, because the nature of the material is to have holes, so we'll still have this phenomenon where an electron will leave and create a hole, but because we started out with holes, there will always be more holes than electrons in the conduction band. Now that's the nature of P material. N material is just the opposite. It is doped with pentavalent material. It will always have more free electrons in the conduction band than holes. And again, even in N-type material, you'll still have the electrons leaving, you'll still have the creation of holes, but because the nature of the material is to have extra electrons, then you will have more free electrons than holes. Okay, this concludes our discussion of doped silicon, and we considered pure semiconductors, we looked at P material, and we looked at N material.